All right, guys, I think let's revisit very quickly the semester calendar just to see where we are. So today apparently is the last class before the reading week. I think we're on good track. Okay, that's good. So I'm going to release your lab number 3 next Tuesday. So happy Thanksgiving after Monday, and then you'll receive the lab 3. So I'm going to give you something to think about. And also, maybe around Tuesday as well, I'll give you the guidance and also the some example question for your written test number 1, which will happen during the lab time on the 22nd. And it's going to be in the Williamsburg Center like the last time. Please don't go to the official room in the Lassang building. I'll confirm. So I'm thinking that tentatively we can host maybe a review session, maybe during the reading week, most likely Friday. I guess maybe many of you wouldn't commute. Maybe I can make it over Zoom. Maybe that could make it maybe a little easier for everybody. You know, it's okay. I think I can make it over Zoom. Can be easier for me as well. All right, so I'll confirm about the details. Most likely in the afternoon. Okay. All right, so I think that's it. And then, yep. Okay, good. And then for sure, towards the end of the reading week or shortly after the reading week, I'll also return back to you the result for your programming test. And after the results are released, if you want to speak to me about the test itself, you're welcome to. Please just drop by my office hour after the reading week. During the reading week, I'll also host an office hour as well on campus. I will possibly open my Zoom meeting room as well. You can also join in. I'll give you some hours to select. Okay, I'll try to make myself available to some hours. Okay, you can still speak to me. All right, any questions? Yes. It will be recorded, yes, yeah. Because that's going to be over Zoom. Of course, I'll record it. Yeah, not a problem. Good. All right, and let's now do a recap. And then today we'll talk about, hopefully we can get to talk a little bit about sequence calculus. We'll talk about it, okay? A little bit. Oh, sorry, wrong side. There we go. All right, so last time we finished off the last example about math review. Oh, so if your written test number 1, most likely it will only cover, well, I shouldn't say only. It will cover lab 1, lab 2, and also your math review lecture. You can definitely study for that. I don't think we have covered enough about the bridge controller just yet to really cover. Maybe I'll save that for your written test number 2 later. So you can definitely get started. But I'll confirm the exact coverage. So last time we talked about how you can formulate programming array using functions. Especially, you want to think about partial function versus partial injection, right? So these are the 2 modeling decisions we talk about. And we talk about other decisions as well. Especially, what about the function being surjective, right? We also talk about why the modeling decision may not be feasible if you choose the wrong type, right? Like a Z, like a set of all integers, which is infinite, right? Those things. And then, oh, another question which I didn't ask. Is it appropriate if I say the names array is going to be a relation between integer and string? Is it appropriate modeling decision? If you don't think so, why not? So you got to think about what would a relation allowed, but it will be disallowed by a function. Diego.
There is no way single in this of an array can hold more than one.
Yeah, exactly. Good, very good. So guys, I'll just hand wave a little bit. If you declare the names to be a member of this, a relation between integer and also string, for example. So here, integers are just domain, right? In that way, you're saying that it is possible for a particular index to store more than 1 values. It's definitely not possible, right? So relation is not even correct, the modeling decision. All right, so that's something you want to keep in mind as well. It's a little bit similar to that where is function that we spoke about in the math review slide. So when you review that, you can also draw some connection. All right, and then we talk about the bridge controller. So this is very important concept about correct by construction. So basically the idea is you do not want to have a single Superman model that's going to contain everything you want to prove about the system. You want to somehow distribute the properties or E description, R description into a pipeline of model. Maybe from M0, we're only handling R2, and then we handle maybe R1 in the subsequent model, one by one, okay? The idea would be individual models should be feasible and manageable for you to specify and also to verify. That's something we'll see for sure. Okay? Especially for our bridge controller, M0 is incredibly simple, only one variable. That's something we'll see. Okay? So just review the idea about correct by construction. That's really the theme for this particular course, which is got a pipeline of models for you to construct. Exactly how many models you want to have is completely up to the need for your developments. And then we talk about state space. It's really just about how complex your model is. The more variables and the more constants you have in your model, the state space is going to be larger, which is going to make it more difficult or less feasible for you to really verify. Okay? So conceptually, think about the state space. It's going to be the list of all the relevant variables and constants such that the typing constraint and also invariance are satisfied. It's going to be a very big set. However, in this course, luckily, we are not really trying to really do anything on the machine. We are only doing manual proof based on inference rules. So it doesn't really matter if the types themselves are infinite. That's the advantage. But for those of you who might be taking a 4315, if you're in software engineering, maybe next semester, in 4315, you will actually see, in order to do something on the machine, to do something called model checking, you will actually have to restrict the type of your variable to be something manageable, right? That's something you will see later, okay? So 4315, 3342 is a very nice sequence of 4 method courses for you to just get some perspective. Anyway, state space. And we talk about the requirements documents, right? We got a series of E description and R description. As far as our M0 is concerned, we're only looking at requirements number 2, which is about the number of cards on the bridge and the island is limited. More specifically for M0, we don't even distinguish between the bridge and the island. It's a compound, right? Imagine that we are seeing the compound found very, very high on the sky. We don't even see the bridge, okay, just for M0. And later on, once we get to M1, when we talk about refinements, we're going to introduce the concept about one-way bridge. That's something we'll see, maybe a few weeks later, not yet, right? Okay, so the diagram you want to remember for M0 is this diagram. We don't really distinguish between island and the bridge. It's a single compound. One example would be, this is also important, let's say realistically, if we got certain number of cards in the island, we also got certain number of cards in the bridge. As far as M0 is concerned, we don't really distinguish the 100 from the 3. They're all considered together, so only consider 103. So somehow the number of cards in this compound here should be bounded by some maximum capacity. That's something we'll see in the constant, right? Just remember that. That's the essence for abstraction for M0. All right, so that's something we also introduced last time. So we got very simple state space, actually. So we got some constant D, and then we got some variable M. These are the only 2 quantities we use to actually somehow to reflect requirements number 2, just about the number of cars being limited in the island and the bridge. And we got some typing constraint. D is a natural number, and also N is also a natural number. And it is important to note the number of cars in the bridge and the island, which is N, should be upper bounded by the D, the constant, right? That's the most important thing to remember, okay? We're going to see some example about how you can, we'll see the various concepts. Right, so this is the last page that we spoke about, right? I'm going to continue from here, okay? It's a duplicate here. So we got 2 events. Okay, we got constant, variables, axiom, and invariance, good. And that's an abstraction diagram, right? Okay, we got 2 events. One is called ML out. Again, ML here stands for mainland, okay? ML out simply means you got 1 card that leaves out of the mainland, right? In that case, the number of cards in this compound here is going to be incremented by 1. So that's why you see M colon equal M plus 1. I will also try to clarify today what colon equal really means. So there is some formal meaning behind that we're going to understand. I'll give you some example, okay? Another event we have is called MLN. That simply means the opposite way. If a car actually goes from the compound back to the mainland, goes back into the mainland, it's going to be called MLN. In that case, the number of cars over here is going to be decremented by 1. So that's why you see decremented. At this point, we have no guards for either this event or this event. You don't see anything about, oh, maybe I can only have ML out enabled if N is somehow less than or equal to some number. I didn't say anything like that, right? So just live with that initial model, okay? So let's now take a quick look on some definition on the slides, and then we'll do some example, okay? Okay, the first one. Okay, so here, we want to think about once you build the static part and dynamic part of your machine, things are going to be run as an abstract state machine. Let's go over some terms, and then we'll see example. Okay, we got the term ASM, abstract state machine, is going to evolve by actions of enable events. So every event you're talking about, think about whether or not it's enabled. If an event is even disabled, you cannot really execute its action. So it's got to be enabled. That's something we'll see. Okay? And then you want to make sure it's subject to invariance. Think about invariance are the integrity of your system. It should not be compromised by any of the events. If ever the invariance may be compromised by certain event actions, there's something wrong of your model. Okay? That's something we'll see. All right, so given states, and then we got enable if the guard evaluated true, disable if the guard evaluated false, and then if that's enabled, we can make some transition to change the state. All right, let's now see two examples. Okay, the simple one here first. So what we said earlier was this ML and MLN. The design is simply inappropriate because you shouldn't really have any events that's godless, it's like an enable all the time. You shouldn't have that. You can easily maybe change your variable in a way that's going to break some invariance. Okay? So let me give you one example here. So that's a question I kind of posed to everybody, right? Is there a trace of event that can lead to invariant violation, right? For example, you can see if ML out over here is simply unlimited. In that way, that means I can keep adding car into the compound over here without any constraint. I'm pretty sure eventually I'm going to break that maximum, that cap size, right? So let's say we have something here. Let's have some example. Let's say we got the maximum capacity being D. So remember the implicit constraint we have is N should be less than or equal to D. Let's remember that, right? That's the main safety property we want to maintain. It shouldn't be violated, okay? So what we're going to do is, let's now try to visualize what's going to happen at the runtime. Well, runtime or when the abstract machine is actually going to be put into life, okay? Let's now start with initial states. So usually for the initial states, we're going to say it's an arrow here. Just simply means we start with that. The constant D is always going to remain to be 2, so I don't change it. But initial value for N will just be 0. No cars has been going into the compound. Let's say we got one occurrence of ML out. One. Oh, at this point here, you also got to think about this particular state space. You want to ask yourself, in order for me to really have ML out happening, the guard of ML must be evaluated to true. Is it the case? Always, because there's no guard, right? In the second example, I'll show you there might be some guard. At the moment, you can see no guards, always enable ML out. So that means ML can just keep happening indefinitely. Okay? So you can think about right here, the ML out guard is true. It doesn't really matter what the state value is. After this, you're going to go into another state right here. Okay? So after N is incremented by 1, it's now going to be 1. Right here. All right? And then, okay, as far as the invariant is concerned, remember we were trying to evaluate this particular invariant. N should be less than or equal to D, right? So this initial state here, 0 is less than or equal to 2. So that's a safe state. For a safe state, I'm going to just color that as green, just to say it is safe. So this state here is safe. What about after the first ML out? 1 is less than or equal to 2. It's also safe. So far, so good. Okay? So now, can another ML out happen? Indeed, because its guard is always enabled. Okay, let's do another one. right here. So let's have another ML out. So right here, oh, sorry. So here, I got another ML out. ML out simply because this particular state here, the ML out guard is also true. That means it's enabled again. It's always enabled. Okay, after the second occurrence, we're going to increment from 1 to 2. Okay, and you can see that 2 less than or equal to 2, invariant here, is also satisfied. We're still fine. Let's see the next one, and we shall see something critical. Okay, so here we have right here. And we know that this particular state, we still have the ML out still enabled. That means one more occurrence of ML out. That one there is actually going to give you ML out, and then that one there is actually going to lead you to a state where n will be incremented from 2 to 3. And this case, the invariance 3 less than or equal to 2 is simply false. So that's an unsafe state. As long as you can find an event trace that's going to lead you to some unsafe states, you know that there's something wrong with your model. Okay? It's a very intuitive way to really justify. But it's not a way to really go very far, because you can see it's very kind of tedious to draw the diagram. But it's good to just get some intuition. Okay, so this one here is going to be unsafe states. So the conclusion we have is this. Okay, I'll put a star here. Okay. If n unsafe states is possible, that means something wrong with the model. Exactly what is wrong, we have to see, right? But as I hinted, the fact that we don't really have any guards for MLL and for MLN is really the issue. Okay? But just based on the diagram, we don't know exactly how to fix it. So the best way to really fix your model design is to really somehow have a systematic way to generate the proof obligation and try to study the proof obligation. Those proof obligations should not be able to be shown as provable because the model is wrong. And based on those unprovable proof obligation, we can see how we can fix the model. It will be more informed information for us. We'll see a little bit later. Are we okay with this? Good. All right. Let's now do another very quick example. Okay. Let's say another one very quickly, just about enable, disable. Okay. So let's say we have the assumption. Okay. So just remind us, we have the action for ML out. We know that n becomes n plus 1. For now, just understand this as becomes. And I will give it some formal meaning very soon. Becomes. What you really want to avoid thinking about this call and equal here is like a variable assignments. Not exactly, okay? But I'll explain why. And also the guard. Let's change the guard. So guard for ML out. Let's say it's simply n less than or equal to 1. Let's change that just for now. Let's say it's always, well, that is always like up to and including 1. Let's say. I just want to see how the model is going to evolve. Okay. Let's now try to see if we can build some state diagram from the beginning, just using ML out. So let's say this. Initially, we have our states over here. So think about this is D. Okay? So D is equal to 1, and also N is equal to 0. All right? In the beginning, 0 less than or equal to 1. This means MLL is enabled. Right? I'm just evaluating the guard right here, right? Just evaluating this, okay? So you can think about 0 less than or equal to 1. So I can definitely go ahead and let it happen. And then we're going to have one occurrence of ML out. And that one there is going to result in another state right here. D remains to be 1. Let's say n equals 1. Right? And this one here, we know that. Let me just make it slightly more interesting. Okay, let me do it again. Let's use a different D value. Oh, sorry. Okay, somehow it's gone. Let me just do it very quickly. Let's say D here is equal to 3. Okay, and then we got n is equal to 0. Okay, that's the beginning. Okay, and then so here ML out enable because 0 is less than or equal to 1. Okay, it's enabled. Okay, is it a safe state? It is, because let me just put it here. This state here is safe because 0 is less than or equal to 3. If you remember, n is less than or equal to d. So here you can see this one is hard-coded. It just always just less than or equal to 1, just for the guard, right? But for the invariance, you still need to evaluate n less than or equal to d. Okay? And then for this one here, let me just change the constant here. And then this one here will just be 3. Okay? So now let's talk about two things. Based on this value here, 1 is less than or equal to 1. So I know that ML out is still enabled from this state. Okay, and I also know that this state here is also safe because 1 is less than or equal to 3. Right? You can see n is less than or equal to d. Right? I'm talking about two things: the state being safe and also the event being enabled. Right? There are two things over here. All right, since it is enabled, I can do one more. Okay, I can do one more ML out. Right here. D remains to be 3, and n is not equal to 2. All right, now watch out what's going to happen. Okay, so as far as the safe is state is concerned, right here. So this one here, it is still safe because n is less than or equal to d. 2 is less than or equal to 3. That's okay. It's safe. However, can ML out happen once more? That's a question. The answer is it cannot. Because if you look at a value right now, which is 2, and if you connect that to right here. Based on the definition for the guard, we know that 2 less than or equal to 1 is false. So ML out, even though it's still safe to do so, we cannot let it happen anymore because of the guard. Okay? So I'm going to write it down. So here, ML out is disabled because 2 less than or equal to 1 is false. So even though it is safe for n to be incremented once more. Because if you think about, if you simply want to increment from 2 to 3, it's still safe. However, ML out cannot happen anymore because of the guard, the design of the guard. So how far you can reach in the state really depends on the guard itself. Okay. Okay, I'm running out of space. ML out cannot happen anymore because it is disabled already. Okay, let me recap very quickly and then we can move on. So in this example here, I'm trying to talk about two things separately. Okay? Number one is about the states being safe, in which case you have to evaluate the invariance n less than or equal to d. In that case, 0 less than or equal to 3, 1 less than or equal to 3, 2 is also fine. Even if I got 3 and 3, that's also fine. However, as far as the state transition diagram is concerned, this state here is not possible for this particular model because the event guard right here wouldn't allow one more MLR to happen because the event is disabled. So think about this issue here, right? So two independence. So think about two independence concerns. The safe states also enabled events. Two separate things. Okay. Any questions here? Yes.
Yeah, so isn't the d equals 3 n equals 0 is the initial state?
N equals 0, yes.
So why would you have an arrow in front of it? Like, does that arrow represent a transition?
So yeah, so just a convention for state diagram. You can think about, let's say here, when I make a transition right here, right? I'm saying that MLR happened. When it first happened, we got this particular value. It's called pre-state, which I will talk about very soon. Okay. After MLR happened, this is called post-states, right? So basically, before and after it happened. Yeah. Initial state is basically only the initialization event will actually happen. If you remember in rodent, there's initialization events, right? So we're saying that after initialization event happened, you got this particular initial states. But there's nothing before the initialization states.
So it's from nothing to initial state.
Yeah, think about from undefined into something that's defined for the very first time. Yeah. Mm-hmm. Good. All right. All right, let's now move on. Okay. Okay, let's now try to introduce some very important concept. Okay. It's called the before-after predicates. Let's talk about it. Okay, so we're done with this. The second event here is about MLN. So it can be shown in a very similar way. So because MLN is also always enabled, so you can easily create an event trace that's going to compromise the invariance. I'll leave that study to you, okay? Very simple to show. All right, before-after predicates. Let's talk about it, okay? Let's go over some bullet points, and then we'll get to the example. Okay, so whenever an event is enabled, so we talk about if an event is enabled, then its action might occur before it occurs and after it occurs. There are two states we got to understand. Okay? So before it occurs, it's called a pre or before states. After the action occurs, it's called after or post states. I'll write it down. Okay, just get some idea. And then we say that the action is basically doing some transition from the before states into the after states. But how do you somehow characterize about the relationship between the pre and post states? You have to use something called before-after predicates. And we have to use the before-after predicate to state the proof obligation later. So let's now just go into this idea first, okay? So let's now take a look. Let's review what we knew from before. So this is what you guys had to write in rodent, right? So for example, these are what you have to write in rodent. And for now, just understand this one here is really becomes. Okay? That's the best way to understand becomes. And then, what's really on the left-hand side over here is what we said. It's saying in the post states, after the event happens. This is the post states value of n. And this one here is saying that it is the same as the pre-states value of n plus 1. Okay, let's visualize that right away. Okay, what do I mean by that? So what I'm saying is, let's imagine we have two states here. One state here. This is another state. Okay? And then I know that MLL is enabled. Given that it's enabled, MLL is going to happen. Okay? Before it happens, we call that the pre-states. Or you can say it's the before states. Either way. And after MLL action happened, you can say that it's the post states. Or you can say it is the after states. Okay, either way. All right, so now we are saying that, let's say, for example, if the pre-state value we have n is equal to, let's say, 2. Let's say. After that, I know that n is equal to 3, just added by 1, right? So what I'm saying is the post-state value of n becomes the pre-state value here plus 1. Straightforward. However, to really make it very kind of, we don't really want to call n and n. It could be confusing about which state are you talking about, right? So what we have is this, the convention. Okay, let me write down the principle first. For each variable x, of course, n could be the x. We're going to write just x itself to denote its pre-state value. And what about the post-state value? We're going to use a different name. X prime. And I'm going to write x prime to denote its post-state value. Okay, so let me just maybe change this one here to be green. Okay, so we got two notions here, and then we'll do example. So we have x over here is about pre-state value. And we got x prime here is about the post-state value. Okay, so think about what we have here is this one here, n equals 3. Rather than saying that, we say n prime is equal to 3, the post-state value. Okay, and now the way to understand this colon equal here formally is like this. We say that n prime is equal to n plus 1. We say that between the actions of m out, the post-state value for n is exactly the pre-state value of n plus 1. We talk about the same variable, but before and after the transition. Okay? So some quick annotation. So n prime here is the post-states value. And the n here is the pre-state value. Like that. Right? Any question here? Question?
So for the guard that you mentioned, should it happen before the event?
Very good question. It's a very good question. Your fellow student just asked, what about a guard? Is the guard evaluated in the pre-state or post-state? If you think about the transition here, I'm going to write it down as well. So what's going to happen is, to decide whether or not this can be the pre-states for MLL to happen, we have to evaluate right here if the guard for MLL is enabled. If it is, and we can go ahead and then try to execute the actions and then go to the post-states. So in the pre-state, we evaluate the guard.
So for the past slide, when we were
Mm-hmm.
Would that not have happened because it's greater than 1, so the event wouldn't have been enabled?
I'll get there. So let me just write one thing first. Okay, the guard of ML out should be enabled. Otherwise, the transition wouldn't happen. Yeah, say it again, please.
So, like, once n was equivalent to 1,
Let's say
then the guard was enabled, and then once it got to 2 is when it.
disable. Exactly. Yeah, very good. So, okay, let's review this right away. In order for this ML out to happen, the pre-state over here, 1 here, less than or equal to 1. So it's enabled. So now, let's say we got this state here. In order for this to be a valid pre-state for ML out, we evaluate 2 less than or equal to 1 is false. So we know that this is disabled. So it cannot be a valid pre-state for another ML out. Yeah. Good. Awesome. I like that. Good. Okay. So guys, I would suggest we do one simple example right away. We can save the more complicated one either after the break or maybe after the reading week, either one. Okay. Let's do this one here. All right. A very common misconception. Okay. Let's say we have an event called swap. Let's say, all right? And then the question is, are these event actions here for swap suitable for a specification between the values of x and y? Let's say we got temp, we got x and y. They're all declared as integer, let's say. I got one hint for you. The way to really think about this is you want to think about the left-hand side, temp, x, and y, they all denote the post-state value for the swap. On the right-hand side, they all denote the pre-state value for the swap. That's how we understand about events, action. Okay? I'll help you a little bit, and then I'll let you think a little bit more. Okay? So to visualize this, think about we got, let's say swap is unconditional, right? It's always enabled. We can always do a swap between any arbitrary variables, x and y. So this is the pre-states, and this is the post-states. So right here, the temp, and also x, and also y, they all refer to the post-states. And the x, the y, and the temp, they all refer to the pre-states. All right? Maybe that's already a big hint to kind of let you know at least whether or not this swap here is really doing what we think it should be doing. Is it doing the right thing or not really?
No.
No, right?
Yeah, because of the time.
The temp.
They don't represent the same thing.
Okay. Let's now try to make it a little bit easier for us to understand. Right? Let's use the prime. It's going to be much easier. In the pre-state, for the swap, we should talk about x, y, and also temp. In the post-states, we should really talk about x prime, y prime, and temp prime. As easy as that, right? In the post-state, we talk about the same variable, but we add some annotation, okay? And then, this one here, what we should do is convert this into the before-after predicates, okay? So, by the way, so before-after predicate is right here. That's what we said earlier about prime and also non-prime, okay? The before-after predicate looks like this. Looks like this, okay? Temp prime equals x. And so each new line is more like a conjunction, okay? Implicitly, okay? And also we got x prime equals y, and also y prime equals temp. So that's how we characterize a formal relation between the x and y and temp, right? So let's say, for example, if I have in the pre-states, let's say x is 23, y is 46, and temp is simply -1, let's say, for example. According to the before-after predicate, what's going to be the post-state value? Let's start one by one. What's going to be x prime? X prime is simply going to be y. And the y here is the initial value for y. It's going to be 46. And what about y prime? It's going to be temp, right? Temp initial value is -1. What about temp prime? Temp prime, here it should be initial value or pre-state value for x, which is 23. So this is what really these three events are specifying. It's definitely not a swap, because you can see we can only go from 23 to 46 for x. That's okay. But for y, it's actually go from 46 to -1, but not the 23 we are thinking about. That's the most important thing for you to see. Right? Any question about this or any part you want me to repeat? Go ahead.
So does that mean that for the swap, we don't need the temp at all, we just do x, y?
I'll get there. Okay, that's the next follow-up question. Okay, so guys, just up to now, are you okay with this? Okay, maybe think about this exercise here. So I think the main idea here is to really think about we're doing specification. We are not really doing sequential composition of the variable assignment. That's not what we're doing. We're not doing programming. Not. Okay. So now back to your fellow student. What will be the correct way of specifying the swap? Right? Correct. Let's say a fix. Okay, so I have my swap events, and then begin and also end. So for those of you who somehow have followed so far, the specification will be as easy as this. All you gotta say will be x and y, right? Should be on the left-hand side and the post-state value. X should be y and y should be x. That'll be the right way to go. You don't need a temp. And the before-after predicate that correspond to this. Okay? The before-after predicates simply x prime equals initial value of y, pre-state value of y, and the post-state value of y will be the pre-state value of x. Okay? If we try to apply this example here, right? So now let's say we only got x and y right here. X prime will just be in pre-state value of y, 46. And y prime will just be x. Y prime will just be pre-state value of y. Just try the three. Right? So that's the right way to go. Go ahead, please.
So basically, whenever we have a corner equals, we think of even though we don't have the prime line explicitly
Yeah.
there, we think of the primes like that.
Yeah, that's one way to go. Yeah, I agree with you. So what your fellow student said was, think about this more like a equal, like a mathematical equality. And then on the left-hand side, it's as if you put a prime. That's the way to think about it. And the implicit new line is like a conjunction. Yeah. Question?
So we don't go line by line, it doesn't store anything either, it just does everything at once.
Exactly. Yeah. Another very important insight is, so in Roda, it's more like a specification. So when we talk about conjunction here, there's no sequence over here. So everything happened at one go. There's no sequential happening. Think about everything just happen as a transaction at one go. Yeah. All right, guys, question? Okay, good. Okay, so I would suggest we take a short break, and then by taking attendance, after the break, I want to go maybe directly to sequence calculus a little bit, some introduction. I can leave some tricky example maybe after the reading week, right? All right, so let's now talk about the goal that we want to establish. We may not be able to satisfy that completely before the reading week. I want to give you some idea quickly, okay? So the most important thing we want to achieve is to preserve the invariance. invariant usually should really incorporate, basically reflect about the safety property that we want to maintain for our system. So we got to make sure they're always preserved. Okay, so let's go over some slide. I want to state some predicates, and then we'll go on to talk about sequent calculus syntax. Okay, so let's say we got our ML out and ML in. So these two events, as we kind of intuitively justify, they are not properly designed. For example, ML out, it can simply happen indefinitely, and eventually it's going to break the invariance. Doesn't matter how large the maximum capacity might be, eventually it can break it, right? So we want to avoid that. Right, so this predicate here, I want to state that just to kind of link to back to our math review, and then let's now go do that first. Okay. So let's now see here. So what we really want, what we desire, whenever we want to design a system, right, the model, is let's now use the universal quantification. We're basically saying for every state variable, states, okay, in general, and the state here could be a list of variables, just states. And then we say that the states is part of the state space. So if you think about this part here, it simply means it's within the typing constraint, satisfying the typing constraint. Okay, I'll give you an example in just one moment. And then if it is the case, we want to make sure every possible state is going to satisfy the invariance. So invariance of the states. So you can think about the invariance for our initial model is just this. So these two predicates are the invariance. Specifically for this one here, let's say. Okay? That's our safety property for model 0. So this is our invariance. Okay? So let's say in our example here, we're basically saying for every n, which is our variable, and then satisfying the typing constraint, that's the typing constraint for n. N is a natural number. And then we want to make sure for the invariant part, n is less than or equal to d. N is less than or equal to d, right? How do we disprove this universal quantification? Remember the proving strategy, right, in the math review. In order to disprove a universal quantification, we have to give a witness, right? To disprove it, we have to find a witness. Find a witness states. So maybe in this case n, that is actually in the state space. But that particular state is going to fail the invariance. So not the case, invariance of the states. Okay, it is important for you to note the following. Okay, note this. Okay, it is in the state space, but it does not satisfy it. So we're basically having true implies false, which is false. That's basically what we have. Okay. So this one here is really the strategy where we got the true implies false, which is equivalent to false. So the variable is in the state space. However, some states is going to violate the invariance. So true implies false. Okay. This kind of approach is nice. However, we want to be able to more systematically find out exactly what that witness can be. So that's something we want to see from the proof obligation. That's something we'll gradually build up after the reading week. So for invariant preservation itself, just as a preview, it's going to be formulated as a proof obligation. And the way we're going to express each proof obligation, we have to learn some new syntax, which is not difficult. I'm going to introduce to you about a syntax. And the proof obligation is going to be stated as a sequent. As a sequent. That is something I would like to introduce to you briefly today, before the reading week. Okay, sequence. What exactly is a sequence? We're going to see. All right. Okay, let's now take a look at the next slides, and then we'll switch to talking about syntax. Okay, so sequence. Okay, so before the reading, basics today, we're going to learn a little bit about the syntax and also meaning for the sequence. After the reading week, we're going to apply this sequence for many of the proof obligation and see how we can apply the inference rule and also do some manipulation. Once you have either you succeed in proving some proof obligation, or you fail to really prove it. Either way, we're going to see how what we should do as a consequence. Okay, let's now go on to talk about syntax. Okay, syntax. Okay, so there are two ways to write a sequence. Just to begin with, this symbol here, I'm not too sure you may have seen that before. Have you seen that before in the math course? Okay, maybe that's good. I'll let you know that. It's something called turnstile. It's the name. Okay, turnstile. And it has a historical root about why it's called turnstile. Okay, that's something I just Googled during the break. I want to show to you. If you ever took a subway in Toronto or New York, in the old major city, have you ever seen this kind of thing in the gateway? That one is called a turnstile. And people call this symbol there turnstile because they thought it looks like this gate over here, turnstile. I'm not making this up, it's actually true. Okay, so it's called turnstile. Okay, anyway, if you want to make some field trip, during the reading week to see that, you can give it a try. Okay, anyway, it's called turnstile. And then let's understand what exactly that means. Okay, H and G. Okay, let's talk about it. So there are two ways to really write it. Either you can write like this, turnstile over here, and then put the two things horizontally. Or you can write it here, and then you can put two things vertically. It depends which one is more convenient, but you should just get used to both. Right, let me talk about, so in the case of H, we simply call H the assumptions or hypotheses. Assumptions and hypothesis. Okay? And the H over here, the same H. Just remember, it is a set of predicates. You can have individual predicates, more than one. Can be one, also can be zero, also can be multiple. Just a set of predicates. Predicates simply means you can use a universal, existential, you can also use conjunction, disjunction, implication, etc. Right? All the logical symbols that we spoke about in the math review. Okay? So that's about the H. Assumptions, hypotheses. And for the G here on the right-hand side or downside, it's called the goals or conclusions. The goals or conclusions. And this one here, the G, is also a set of predicates as well. A set of predicates. And let me give you one example right away. Okay? So let's say we have a turnstile. Let's say, for example, okay? Let's say we have a turnstile right here. Let me write it vertically. Okay? Hypotheses or assumptions could be, let me say D is a natural number. And also N is a natural number. And also N less than or equal to D. These might all seem familiar to you, right? But that's okay. We're going to see that. Okay? So these can be assumptions. And then the goal, I'll just put a single predicate, just singleton set, is simply N plus 1 less than or equal to D. So this is a sequence. Okay? That's a syntax. So the syntax is very easy. All you have to remember is you have a symbol called turnstile. And then if you write it horizontally, the left should be the hypothesis, and the right should be the goal or the conclusion. If you write it vertically, so hypothesis should be here, and the goal should be here. Right? That's all you need to know, syntax-wise. And let's now understand what it really means. So that's what I meant by semantics, the meaning. Okay, let's now talk about, semantics is just about the meaning. The meaning of a sequence. Okay. If I write H turnstile G itself is going to be either true or false, first of all. Itself, whenever I got a sequence, it's going to be either true or false. True or false. It's always a predicate, actually. So the definition is H turnstile G if and only if and only if, you'll be a little bit surprised, it's just something you're familiar with. Simply, H implies G. It's basically an implication. Okay? And the informal, let me write it down in English as well. Assuming that H is true, G is provable. We should be able to prove G, assuming that H is the case. If we cannot do it, we got to see some feedback from there. That's something we'll see how to interpret when the sequence cannot be proved as true. Okay? And let's see, I think there's some terms I can mention from the slides. Yeah, so you can also say H entails G, or you can say H yields G as well. So it's kind of up to you. Or just say turnstile, that's okay too. Okay? Let's now talk about some important question. Right here. That should be rather easy to answer based on the implication property. Okay? So what does it really mean? When H over here, remember we say it's a set of predicates. What about its empty set? If I write something like this, turnstile G. I want to know what this really means. If I don't really have H over here, would it be as if H is maybe true or is false? Right? Let me give you two options here. Think about it. Okay? So option number one. It is equivalent to true turnstile G. That's option number one. Okay? And option number two. False turnstile G. So when H is simply empty, it's not there, it's absent. Which option should be the formal meaning for that particular sequence? Okay, hold the answer just yet? Yeah. Just hold it. Okay, 1 or 2? Okay, go ahead, 1 or 2?
I would say 1,
You would say 1?
because there's no assumptions or hypothesis, which means that there's no constraints for
Mhm.
G, so G can be anything that it wants.
Yeah, so yeah, that's pretty much correct. Yeah, so 1, turns out the answer should be 1. Okay, but let's see why. And also, number 2, why number 2 should not be the formal meaning. Okay, let's see both. So this one here, so this should be the answer. Okay, this one here. Think about what this one really means. Okay, let's think about logically. So this one here, we know that if and only if, by definition, true implies G. Remember, we got something called identity of implication, right? So this one here, if and only if, just G. That means in this case, you ought to prove G without any help, without any assumption. There'll be no assumption, basically. Okay? So this one simply means proof G without any assumption. That's the right meaning. Okay? Let's see why number 2 should not be the meaning. Okay? Number 2 here. Can anybody see why number 2 should not be the meaning? Using kind of similar pattern of the reasoning. Go ahead, please.
Because the implication would mean that G is always true, since the first part is false.
Because the implication will always be true. In that way, you really got nothing to prove. Right? Good. Good. Thank you. Yeah, that's exactly correct. All right, so this one here, it would be as if you got actually false, well, if and only if false implies G. And remember, we learned about the zero of implication in the math review, right? So this will be always just true. So that means when you have no hypothesis, you just prove it. That doesn't make sense, okay? So that means no hypothesis means it's proved. Too good to be true, right? Cannot be the case. All right. Okay, we got about 13 minutes. Let me do one more thing. Okay, I want to give you a little bit idea about how this sequence can be somehow used to really formulate some proof obligation. Let's do that quickly. Okay. We'll get the more mathematical stuff maybe after the reading week. Okay. So let's now take a look at one thing here. Okay, I'll just go on directly to the iPad page. Okay, but the slides I'm talking about is right here. Is actually slide number 17, right? So this here is just one example about how we can formulate a proof obligation. However, this one here is even very informal way to really formulate the proof obligation. After the reading week, we are going to see something a little bit more symbolic. That's really the right way to understand, but not today. Today we're kind of exhausted. Maybe on the Tuesday after we come back. Okay. So let's now just get some idea. Let's just try to read about this proof obligation. First of all, let's clarify some acronym here. So when I say PO, it really stands for proof obligation. And also for VC, it's really equivalent term. It's called verification condition. And the one we are trying to formulate is for invariant preservation. So let's say this is our example model, right? Something we just talked about, right? That's something you're already familiar. Let's try to read what the sequence is trying to say. Remember the semantics, right? We say that given the goal, sorry, let me say it again. Given the hypothesis, we want to prove about the goal, right? So here we're saying this. Given the hypotheses, which are 1, 2, and 3, we want to prove that invariant is satisfied. All right, like that, okay? But let's now dive a little bit deeper. What can we assume? We can assume the axiom, which is right here. We can assume the invariance in the pre-states, basically the unprimed version of the invariance, which will be these two. And we can also, since we talk about ML out, so here we talk about invariant preservation just for ML out. Let's say for ML out. Whenever you talk about invariant preservation, you don't really talk about for all the events at one go. You talk about individual event. Can ML out always preserve the invariance, and also can ML in always preserve the invariance? So we only talk about ML out right now. Okay? So the guards of the events right here is ML out that we are focusing on. So we assume the axiom, we assume the invariance in the pre-states. We also assume the guards, because guard is the guard has to be enabled in order for the action to be happening. And what should we prove? We want to prove that somehow the invariant in the post states will be satisfied. Post state is a prime version of the variable, right? Let me do a little bit exercise together with you. I want you to get just exposed to it just for the first time. We're going to see this a lot. The first time might be a little bit confusing, but let's do it, okay? How do we turn this one here using this example model? Let's try that, okay? That's something you will have to do many times, okay? Let's now start with that. First of all, we got a turn style right here. Okay, let's go one by one. First of all, we got the axiom. Axiom here really correspond to the axiom right here. Okay, we just put a predicate. We don't need to put a label. Okay, so we just got the D is a natural number. This is one predicate as part of the hypothesis. And then we say the invariance satisfied in the pre-states. Let me talk about this one as well. Invariant satisfied at the pre-states. So we talk about this invariant over here and also this invariant over here. Okay, let me write it down right here. The invariance we have is like this. N is a natural number. And also n less than or equal to d. Think about the n here is simply just the unprimed version. So that's a pre-states, okay? Unprimed. So think about this is the pre-states version of the invariance. And let's copy and paste the same invariance. And then we talk about invariant prime. In that case, prime every variable. And prime, after whatever transition it might be, after the action, we'll talk about it, is going to be still a natural number. Also, n prime should still be less than or equal to d. Whenever you want to create a post-state version of the invariant, just prime every variable in there. So this one here is the post-state version, okay? So this one here is the post-state version. Eventually, we want to get rid of the prime. Eventually. I will see exactly how to do that. I'll get there in a moment. But now, just want to understand for the invariants, the pre-state version and the post-state version. It's really the same invariant, just that we prime every variable in the post-state version. All right, so the invariant satisfied at the pre-states, this one here. Okay, so we're just going to put n is a natural number. N less than or equal to d. Pre-state version, right? The blue one. And also for M out, also we got its guard. So for that one there, let me use, how about orange? Okay, the guard for the events. And at the moment, there's no guard. It's as if the guard is true. But let me put explicitly true. Okay, so here the guard will be just true. So I will just put true right here. So there are four predicates we can assume. We can assume the axiom. We can assume the pre-state version of the invariance. We can also assume the guard of the ML out. All right? So now, the tricky thing is, what about the post-state version of the invariant? That's something we're going to work out. Okay? Invariance satisfy the post-states. That's something we want to prove. First of all, let's now write it down. This one here is going to be, let me say, is pink. Okay? So I want to go to the same invariant right here. Right here. What I will do is I'm going to, first of all, let's write down the prime version. That one there is right here. I have n prime is a natural number. Okay, let me put it in conjunction. And n prime less than or equal to d. Okay, that's a post-state version. In order for us to prove or to discharge this particular sequence, we want to get rid of all the prime. The way to get rid of it is to figure out the before-after predicates of the corresponding events. Let's do that, okay? Okay, I'll write it down for you. So this one here, I'll put a star. to eliminate the primes. Consider the before-after predicates. Okay, in this case, since we talk about M out, this is the action. And we said earlier, this corresponds to the before-after predicate M prime equals M plus 1. Right? Okay, that's now. First of all, let me copy this down. Okay, and then we do some replacement. M prime, natural number. And also M prime less than or equal to D. In order for me to get rid of the M prime, I know that M prime at the same time is equal to the pre-state value plus 1. I can now replace this one here. Let me just go to, I can replace this one here by M plus 1. I can also replace this one here by M plus 1. That's a post-state version. Somehow post-state version conceptually understand it as the prime version. However, you cannot really have the prime for manipulating the sequence proof. In order to really get to its ultimate form, you have to somehow get rid of the prime using the corresponding before-after predicate. That's something we'll keep doing. That's just for the first time. Okay? So we basically simplify this part over here. Finally, we're going to simplify. Let me use purple. Sorry, I just missed my purple here. There we go. So we're just going to simplify this one into n plus 1 less than or equal to n, and n plus 1 less than or equal to d. Right, let me recap, and then we're done. Okay. So the ultimate answer is we have this sequence here. 1, 2, 3, and 4 are the hypotheses. We assume they are true. And turnstile is more like an implication. We want to prove that n plus 1 should still be a natural number. And also n plus 1 should still be less than or equal to d after the action n plus 1. All right? So during the reading week, let me give you some suggestions. You definitely want to review the math review lecture. So to get prepared for your written test 1, you may also want to maybe get a review again, maybe about the predicate pattern in lab 1 and lab 2. And I'll give you some example questions to try it out for written test 1. For this one here, I would suggest at least try to review a bit about this page over here to see how to manipulate this sequence. Because after the reading week, we're going to also dive deeper into manipulating the sequence. All right, thank you so much, and I'll reach out to you about other things. Okay.